I'm going to start the recording.
Recording stopped.
Okay. Oh. Looks like I hadn't stopped the recording.
Recording in progress.
Okay. So that's all right. Don't really want to put my complaints about Zoom or the ISP, and I don't know which it is, or YouTube, in a video, but since I don't know who's guilty, I just know somebody is. Okay. So, that linear equation, we can dispose of that pretty quickly. It's of the form y prime plus p of x y equals 0. This is homogeneous. And the way I like to annotate it is this is a lowercase p, this is the uppercase p. The uppercase p of x is the integral of lowercase p of x and the key there is just so that y prime equals negative p prime of x e to the negative p of x, okay, and that equals negative little p of x e to the negative big P of x, and of course this is little p of x times e to the negative big P of x, so you have the negative of little p of x multiplied by the e to the exponential plus the positive p of x. Okay, and it works out. It's almost automatic. So I'm not going to say any more about that. That's pretty easy. And then not sure what they use over here. I'm going to use q of x because that's often used. Okay, y prime plus p of x y equals little q of x. Your integrating factor is e to the capital P of x. Then you end up with this, so that this side is the differential of I think I'm writing this correctly. Okay. Now why is this side the differential of this? The differential of e to the p of xy is just by the product rule, the derivative of e to the p of x times y plus y prime e to the capital P of x Yeah, I think that's going to work out. And it equals this side. We don't worry about that. So when I take the derivative of this, I get p prime e to the p of x y plus e to the p of x y prime equals this. And p prime is just little p of x. So I get e to the capital P of x y prime plus little p of x times e to the capital P of x y, and this is just this. Okay, so this is the differential. So now that works out. You want to verify that when you do it by running through these steps just to make sure you've got it right. But once you've got that, you can just kind of say, okay, we don't need that anymore. All we have is this. If the differential of e to the p of x y, and we're talking about the differential with respect to x, equals this, then e to the capital P of x y is the integral of e to the capital P of x q of x. You're going to get an integration constant over here. If you can perform this integral, and you often can, then y equal I'll put a dx in there. Equals this, where again, this is going to be an integral with an integration constant. The integration constant allows you to match an initial condition or a given condition, and the integral just gives you some function. It'll often be a function that's easily divided by this one. And that's how it works out. So this is what you want to remember. Just that you're going to multiply by e to the capital P of x, and that's going to change the left-hand side into a differential. So you can integrate both sides and get your solution. Don't forget your integration constant. Okay, I don't want to take the time to work through the details of an example, because we only have limited time. I don't think that's going to be to your advantage. And we worked through a number of examples early in the semester if you need them. Okay, and you probably don't even need to go back to earlier videos. You probably get plenty of examples from your book, Google, whatever. And I don't see that you have any serious problems with mechanics of doing the integrals and stuff. No more problems than most people would. Okay, so you want to be able to do your integration, and of course you're going to need to show the integration on the test, because you need to show the details, so I know you're not getting it from Wolfram Alpha or something. Even though I trust you, as I've said, that's got to be the standard in any course where you can't proctor your tests. Okay, so that's linear equations, and that's really pretty much what there is to it. Now, of course, you have things like interpretation and just the calculation details. I don't have time to go through a lot of calculation details here. Okay, now the next thing that's kind of logically follows is exact. And then if an equation looks just really terrible, okay, you don't see anything, it's not separable, it's not linear, not first order linear, it's something bizarre, this is often your last recourse. And you just cross your fingers and hope that this thing turns out to be exact, as it does in a lot of really important situations. Okay, exact equations form is df equals 0, but it's going to be disguised. That's disguised, not disgusted. Now, you might be disgusted. The equation doesn't have emotions. Okay, I don't think so anyway. Form is this. Well, df equals 0 means fx dx plus fy dy equals 0. And we write that as, I don't know if we use m or n here. I never can remember, but I'm going to write it, I think it might be n. And I think I have a little better than a 50-50 chance on that, because I always want to call this m, and I'm often wrong. Okay, so n dx plus m dy equals 0. Now the equation might not be in this form. You might have some dx's over here and some dy's over there on the other side. Or you might even have a dy dx plus some awful function. Whatever. But you have to be able to, of course, do the algebra to put it in this form. But I think if you just realize that that's what you need to do, you're not going to have any trouble doing it. So we have n dx plus m dy equals 0, where obviously n is going to be your fx and m is going to be your fy. Okay? If ny equals mx, then there exists an f of xy such that n equals fx, m equals f lowercase y. That's actually an if and only if statement, but I wrote it down this way because that's what you really need to know. Okay? And I'm not really writing this as rigorously as I'd like. And this is because ny is fxy and mx is fyx, and they have to be the same. fxy and fyx are the same. You know that from multivariable calculus. So that's your test. And now the task is to recover your form f. So I can say, thus, f is the integral of ny with respect to x, which is equal to the integral of mx with respect to y. Now, the integral, and look, something doesn't feel right. Let's see. ny equals fxy. So if I integrate ny with respect to y, I should get fx. And that should be n. It's easy to get myself turned around. I'm just making sure that I haven't done so. And it's important to make this connection, which is really straightforward and trivial, and something's just going haywire here, so let's make sure. And it's certainly not so. Because if n equals fx, then f is going to be the integral of f with respect to x, and m is going to be the integral of, f is going to be the integral of n with respect to x, I think that's what I said, and m is going to be the integral of m with respect to y. Okay, so we got integral of nx dx has integration constant I'll call it g of y. Since you're integrating with respect to x, your integration constant, well, any function of y is constant with respect to x. So you're going to get this function, and the integral of my with respect to y has integration constant h of y, h of x. And g of y has to equal h of x. Well, those are your conditions. If you write out the general constant here, g of y, you need this because this integral might give you a function of y that doesn't appear when you do this integral. Okay. Similarly, this integral might give you some function of x that doesn't appear when you do this integral. I said that wrong, but you can figure it out. Okay. This reconciles y functions that appear in the integral of my dx. Now in general, when you integrate my dy, okay, in the integral of my dy, and you know, one thing that I'm finding that my Zoom videos do is they really exaggerate smudges, so I try to avoid them, usually unsuccessfully. Okay, again, this integral m is going to be a function of x and y, so in general when you do this integral you expect to get some things that involve x terms and y terms, and some things that just maybe only involve y terms. Those y terms are not going to appear in this integral. That's why you have to have the g of y up here. And without going into more detail, because I don't have any more board space, and x functions don't have room to write that appear in, but from the integral of nx dx. So, you know, I recommend in preparing for the exam that you work a few of these, review your work on some of them. I hope you've been writing out your work on the web assigned homework. Or, you know, look back at some videos. You can just flip through them sort of and find what you're looking for. But if you understand this statement in terms of a couple of examples, then that kind of locks in the whole process. Okay, well, that's exact equations. You have separable equations, and I'm not going to do too much with separable equations. Broke my red chalk. just a minor tragedy. Both pieces look like they're functional, so that's going to be okay. Just as long as I don't step on them and grind them into the floor. Maybe I'll move them over a little bit. There we go. Okay, separable equations. Typically, it's going to be a dy over f of y equals f of x dx. Okay? And that means the equation is like of the form y prime equals f of x g of y, and I don't want to use f for both functions. So, and let's deal with the smudge here. Takes a little bit to smooth these things out so there's no smudge. Okay. So you just integrate both sides. Etc. Okay. Don't want to say too much about this, but one important equation that's separable. Well, okay. I'm just going to just state a few examples because most of the examples are really straightforward. So, one example is y prime equals ky. Okay, that's like your population model. The rate at which your population changes is some multiple of your population. So natural log of the absolute value of y equals kx. And this could be a plus k or a minus k, depending whether the population's increasing or decreasing. It also applies to financial models. You know, if you have a certain rate of interest or a certain appreciation or depreciation of your principal at a constant rate, or the rate that you predict to be maybe constant based on history or whatever, you can have these things. Okay, so you got natural log of y equals this, so that y equals some multiple of e to the plus or minus kx. And it's not a plus or minus. It's either a plus or it's a minus all the way through. And I'll remind you that, you know, a is arbitrary, and we don't need to say any more about that. So that's one of your standard types of equations. You have to interpret it in a given situation, but it's usually pretty straightforward. This is a pretty straightforward situation. And radioactive decay is another example, and you'd have a minus in front of your k, or your k would itself be a negative number. So that's something that I think is pretty easy. Now, another separable equation is like y prime equals k y times 1 minus y, or L minus y if you wish. That's a logistic equation. And you get dy over y times L minus y equals ky. and you got to apply partial fractions. And then you got to do some algebra. Okay, and you get a solution. And the solution curves, the possible solution curves, have this characteristic. Okay, we approach this limit in a way that can be analyzed with slope diagrams and so forth. It's an autonomous equation, and you want to use those techniques, which we went over in some detail. Okay, I don't have time to, I want to take the time to go over those, but it's something you want to review. And that's maybe all I'm going to say about separable equations. The process is always the same. Doesn't always lead to an exponential solution, obviously. There are other possibilities, but these are a couple of the more prevalent, more important, more commonly encountered cases. Okay. Now I think we've got a little more board space. Actually, we've got two spaces there. Okay. Bernoulli equations. Just like a linear equation, okay, right now, that's a non-homogeneous linear equation. You use your integrating factor and so forth. But now you put this y to the n there. And now it's not. What you do is you let v equal y to the m, and you determine m such that the equation becomes linear in the variable v. Okay. Spoiler alert. This occurs if m equals 1 minus n. I advocate so that you understand better the change of variable process, that you not immediately go to the spoiler here and the things that come away from the spoiler, but work through the details so you see that this does occur. We work through the details. I'm pretty sure we work through the details. I always do. And I always mess it up at one point. Do you think I understand the laws of exponents by now? And I do, but I get careless. So there's some pitfalls there, some algebra pitfalls that I certainly shouldn't be making at this point, but I seem to usually do. I think I might have worked through it correctly this time. And I don't cheat by working it out in advance. That's no fun. Okay, so anyhow, a fairly straightforward process. You let v equal y to the m so that v prime is my to the m minus 1 dx. Okay, or v prime is my to the m minus 1, so that you solve that for y, and it's going to be a 1 over m minus 1 root of v, and substitute that in for y, and so forth. Substitute that in for y prime, substitute substitute v to the 1 over m for y, and work it out. Anyhow, that all works. So then you just change variables, which is what I just change variables, and the change of variables is that y equals v to the 1 over m v, I better write it down, equals y to the m minus 1 v prime equals my to the m minus 1 y prime. I think I tried to say that a minute ago and left something out, but there it is. So y prime equals v prime over m y to the m minus 1. But of course, y is v is y to the m, so that y is v to the 1 over m, so this y to the m minus 1 is write it out carefully. And there's where I always screw up because I'm careless in doing these exponents, but this is going to be v to the m minus 1 over m. Bring it up into the numerator, it's v to the m over m minus 1. Work out the details, if you're working out the details. And magically, linear